All right, then, we'll get started. There were some typos in the problem set, so do download a fresh copy of that. We'll have our usual problem session on Friday. And not everyone responded, so I just tentatively wanted to schedule a makeup lecture for Friday the 13th.
Another one already?
I know, isn't that crazy? Not a bad luck. Anyway, so I'll see what room will be, and I'll send you a message about that. Probably 2540. All right. So shifting gears a little bit today, we've been talking throughout for many weeks now. We've been thinking about the notion of non-classicality, and particularly in quantum optics, and how we think about classical light versus non-classical light. And in particular, we've been thinking about this for the case of a single mode, right? So we have a single mode, and we've been asking about notions of non-classicality, right? And so some of the features we saw about non-classicality include things like self-associated statistics, and negativity of the bigger function. And we've been studying a lot of these different features and trying to categorize the subtleties associated with non-classicality that very much depends upon what we measure, whether we see non-classical features or not. A single mode of the electromagnetic field we think about as a single degree of freedom. So as we've discussed, we think about the modes as the degrees of freedom of the field. And that's how we originally quantized the field when we thought about a decomposition of the field into modes, and each mode was effectively one quantum degree of freedom, which we then quantized. All right. But what things get, of course, more interesting if we think about multiple modes. Which really means multiple degrees of freedom. And the features associated with the light when we have multi-modes is more rich and more complicated, obviously, if we have a single mode, and there are features, of course, that we see when we start talking about multiple modes that we don't see when we think about a single mode, most notably the story of entanglement. And that's what we're going to talk about for the next couple of weeks. We're going to talk about entanglement in the sort of general sense. I think for almost everybody, it's something that you've seen already before in other of your courses, but we'll just level the playing field here and make sure we share a common language and common notation talking about that. Okay. And of course, entanglement, it's really in quantum optics where entanglement was really first observed and put to the test. This quantum optics is the forum in which the foundations of quantum mechanics have been most deeply studied and explored. And so thinking about entanglement in the context of quantum optics is very important, okay? So let's just start from some very basic things, just to make sure we have some of the basic ideas and language and notation on the same page for everybody. So if I just think about 2 degrees of freedom, and let's just first think about this classically. If I have each degree of freedom, we thought about a classical particle. Each degree of freedom is described by some set of canonical coordinates, right? So I might have one canonical coordinate for 1 degree of freedom, say degree A. This could be one particle and another particle, or they could be the position and momentum of a particle in 2 different directions. Those are also 2 degrees of freedom. You could have, say this could be Y coordinate and the piece of Y coordinate of that part. That's also equivalent to 2 degrees of freedom. Okay. So at the moment I'm just thinking about this from the point of view of classical physics, and we can then think about classical dynamics associated with these 2 degrees of freedom. We can think about, say, a Liouville equation, which might have a probability distribution associated with these degrees of freedom. Of course, what we know quantumly, I can't necessarily describe unless we start thinking about bigger functions, which we will, associated with both x and p, but we can think about measuring, say, x on these 2 particles, okay? So I could quantumly say I would have some wave function that describes the joint probability amplitude for measuring the position x on the 2 degrees of freedom, right? And that would then tell me that the probability density for measuring those is given by the square of the wave function. And similarly, I could think about the joint momentum space wave function. And think about the probability density for measuring the joint outcomes of momentum on the 2 particles, right? So this is standard quantum mechanics, and of course, the momentum space wave function is the Fourier transform of the position space wave function. And from these, I could think about marginal distribution. So if I wanted to ask what is the probability of measuring, so this is a joint, let me put some labels here. This is a wave function associated with the joint system of the 2 degrees of freedom A and B. This is the joint probability distribution of these 2 guys. And I can think about a marginal distribution, which is to say, if I integrate out particle B, this would tell me, oops, there's no tilde here. This would tell me the probability distribution for measuring where particle A is, irrespective of where particle B is. That's what we would call the marginal distribution. And similarly, I can marginalize by integrating out the position of particle A, and that would give me the probability distribution for measuring particle B. These are what we call the marginal distributions. And similarly, I can marginalize out the joint momentum distribution, right? Very good. So a first question I can ask myself is, if I marginalize, so given the marginal, say, marginal distributions for, say, position and momentum for particle A, does or is there a wave function which has a position momentum space such that this equals the square of this, and this equals the square of this, where this is the Fourier transform of that. So my question to you is, what is the answer to this? So if I give you the marginal distribution, meaning the marginal probability distribution for measuring the particle A, either in the position, either measuring its position or measuring its momentum, is there a wave function that tells me what that probability is? Yes?
Would it depend on if X and A and B are pure?
Okay, so it's a good point. Right now, I'm taking this to be that there is a pure state. So there is a pure state. Let's restrict our attention to that. That is the joint wave function, the joint probability amplitude. I could either look at the wave function, say, in the position basis, measuring position, or I can think about momentum. So there is a joint overall wave function, and I've then given that wave function, I can marginalize it and ask about, this is just classical statistics. It says if I want to look at the probability of measuring one of the random variables, irrespective of the other, I just integrate out the other one. That's what we call marginalizing the probability distribution. So my question to you is, given the marginals, and under the assumption that, as Nate suggested, that the overall state is pure, does there exist a wave function that determines those probability distributions? Meaning, there's a wave function, I'm calling it psi sub A, in the x basis, and this is its Fourier transform. Yeah.
Is it meaningful to try and just marginalize the wave function?
No, that's interesting. No, because the marginals are about the probabilities, not the probability amplitudes. Okay.
Would it be an ensemble of wave functions?
So there is a situation where this is true, and there are situations where it's not true. So the answer is sometimes. And what is the condition when it is true? When is the answer yes?
Whether or not.
If it's a product state, right? So if it's true, the answer is if and only if the joint distribution, that's to say the joint wave function, is the product of a wave function for that and some wave function for that. If this is true, if the joint wave function factorizes, well then we see that this is true.
Oh, did you mean PR of B and XB? Given a marginal of XA and PR of
Yeah.
XB?
Last line.
Or the first line? Or,
I'm sorry.
Given marginal PR of XA, and did you mean PR?
No, I'm saying I have the marginal distribution. These two marginal, I have marginal distribution for this and equivalent marginal distribution in momentum. Okay.
So we're just talking about.
I'm talking, I have 1 degree of freedom, and that 1 degree of freedom, I want to be able to predict any measurement I could do on subsystem A. Okay, so in this case, the two measurements I'm doing are position or momentum measurements. So given the joint wave functions that we have over here, I have the marginal distributions, and I'm asking under what condition is that probability distribution just the square of the wave function?
Should that be phi b x b?
Yeah, this should be x, b. Thank you. Yeah. So, if that's true, that this is a product state. And the joint probability distribution, which is the square of the wave function, is just the product of the probability distributions, which is just the square of each of those wave functions, okay? So, if the state is a product state, then we say that the joint probability of measuring these outcomes is uncorrelated. These are statistically uncorrelated. If this is not true, if they're statistically correlated, then in quantum mechanics, there's something more than just being statistically correlated. We're going to say otherwise, if this is not true, if the wave function, if the state does not factorize in this way, they're statistically correlated, but more importantly, they're entangled. Okay, yeah?
If it's entangled, you could still find like a mixed state that satisfies that, right?
That's right. So wasn't really, we'll come back to that in a moment. Absolutely, that's true. The question is, but is there a wave function? And the answer is no. There is no wave function that I could write down such that its Fourier transform gives me the right probability distribution in momentum. Okay. Now, you're absolutely right. You're right. We all know, many of us know the relationship here, that there is a notion of a marginal state, which will be more general than a wave function, as Anne said, an ensemble wave function is a mixed state. We'll review that in just a moment. Okay? So that's interesting. Number one point here. Okay? So if I can have a situation where I have a perfect description of the state in terms of something which is pure, but yet its marginals, there is no pure state description of it. Okay? That's one of the hallmarks of entanglement. All right, so we wanted, was just thinking about this from the simple picture of thinking about probability distributions on continuous variables. Let's formalize this as we know the formal description of this. Is in terms of the tensor product structure of Hilbert space. All right, so let's just quickly review some of that notation. So I can think about a degree of freedom that we had in classical physics. In quantum mechanics, we call it a subsystem. They're one and the same thing, okay? So we think about the whole system and subsystem. Each subsystem represents a degree of freedom. And when I'm talking about this, I'm talking about distinguishable degrees of freedom. The whole story about identical particles is complicated. And at that point, a lot of the structure breaks down. I just want you to keep that in the back of your mind. For the moment, we're thinking about distinguishable degrees of freedom, okay? And effectively, of course, even if I have, say, 2 electrons, we know that they are indistinguishable particles, but they become effectively distinguishable if they're never overlap spatially with one another. If they never overlap spatially with one another, then for all intents and purposes, the effects that are different, that are associated with identical particles versus distributed particles is irrelevant, okay? So when we think about distinguishable degrees of freedom, we're saying they can be effectively distinguishable too, all right? So when we have that, and I think about, say, two subsystems, they have two parts, that's a bipartite system, then the joint Hilbert space we write as the tensor product of the two Hilbert spaces, one for subsystem A and one for subsystem B. And each of these Hilbert spaces could describe a system with a certain dimension of the Hilbert space. They don't have to be the same dimension. I could have dimension A for subsystem A and dimension B for subsystem B. And the notion of the tensor products structure is the following. So if I have a state psi A that's in Hilbert space A and a state psi B that is in Hilbert space HB, then we define that there is a state which is the tensor product, I'll call this phi, is equal to some state in the joint Hilbert space. Okay? So we have this tensor product operation. Abstractly, we can just take any two vectors in each of the spaces, take their tensor product together, and that by definition is a state in the tensor product space. Moreover, it's bilinear. So that is to say, if I looked at the superposition of two states in Hilbert space A and took its tensor product with a state in Hilbert space B, then it distributes through linearly. And that is the superposition of the tensor products. Okay, so that's one of the features of the tensor product space. And similarly, if I took the superposition on B, okay, so it's got this bilinear kind of features associated with it. Right, okay. I guess I used the word over here. Let's continue on this side. We can think about a basis for a joint Hilbert space. Okay, so if the states B sub I are a basis for Hilbert space A, and F sub J are a basis for H sub B, then I'll call I comma J a B defined as the tensor product of the basis vectors is a basis for the joint Hilbert space, right? And so first question, what is the dimension of the joint Hilbert space? It's the product. We can see that right here, okay? So the dimension of this is the product of the dimensions of the two Hilbert spaces, okay? And so I can express any state in this basis, okay? And so just quick reminder of notation here. So let's say that I write psi in Hilbert space A as a column vector with coefficients alpha sub I being the probability probability amplitudes associated with the basis E sub I, and I have a state on Hilbert space D, which has amplitudes beta, which are the inner product with the basis vectors f sub j. And now I want to know if I write psi as the tensor product of these guys, and I want to write it in the basis ij, how do I do it? So this is the tensor product of this column vector with that column vector. Okay? So this is the Deutsch notation. The dot on top means a representation of this particular basis, and that basis is given by the tensor product of these two. So what is the operation for the particular ordering that we take that allows me to take the tensor product of these guys? So the way we do it is each one of these column vectors gets put in this. So I have alpha 1 times beta 1 dot 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 BD, alpha 2 beta 1 dot 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 beta BD dot 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 alpha BA beta 1 dot 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 beta D sub B. So that's equal to alpha 1 beta 1 alpha 1 beta 2 dot 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 alpha 1 beta D sub B dot 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 alpha 1 alpha D sub A beta 1 dot 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 alpha D sub A beta D sub B. Okay? That's how I always think about how you take a tensor product. You shove them in that way. That's the rule back in the ordering that we take. All right? And you can see that this column has D sub A times D sub B different entries. Okay? All right. Let's think about marginals. Okay. So let's say that I have some, I'm going to be, let's see, how I want to think about this for a moment. Okay, so let's be completely general for a moment. I could have, let's say I have a state, rho AB. It could be, if it's pure, that state is this. But it doesn't have to be pure, but let's start with that, okay? So I can ask, what is the probability of measuring outcomes, say, labeled by the basis vectors? So the probability of measuring outcome I on subsystem A and the probability of measuring outcome J on subsystem B. How would you calculate that probability? Yeah.
Is it just the ij element of the density matrix?
That's right. It's the diagonal matrix element of the density operator. If this is a pure state, of course, this is just the square of the amplitude of the wave function, right? This is one and the same thing, okay? So this is my joint probability distribution. And if I wanted to ask then about the marginal probability distribution. What's the probability of measuring outcome I on system A, on subsystem A, irrespective of what I might measure on B? Then according to the rules of probability, I marginalize by summing over all the possible outcomes of subsystem B, and that's the marginal distribution. Okay, everyone clear on that? So if I look at that, that is equal to the sum over J, I, J, rho A, B, I, comma, J. Right? So now this is sort of comes to Leroy's point. How should I think about this problem? Is there a state associated with subsystem A that gives me this probability distribution? Well, generally, it's not going to be a pure state. Generally, there's no wave function, but there's something more general than that. And we can just see that right here. Again, these vectors are those tensor products. So I'm going to write out this a little bit more carefully. I'm going to write it, we take these different notations all the time. So AB, rho, AB. Which is equal to this, where rho A is given by thus the sum over J, Fj, rho AB, Fj. Everyone see that? That this equals this, right? And so what is this object? So we remember, as we said earlier, the expected value, the probability of the outcome here is this matrix element. If we sum over all I over here, then this would be equal to the trace of that, which would be 1, right? If we summed over all of those values, that probability distribution, if it's normalized, is equal to the trace of the overall density matrix. This is not summing over both I and J, so it's not the trace, it's the partial trace, okay? So what we write this is the trace over B of rho AB. So this operation, the partial trace, is the equivalent of marginalization. The partial trace is equivalent to marginalization. All right, very good. So now to the question at hand. Under what circumstance is there a pure state which, so is rho A what's the answer? The answer is sometimes. And the answer is if and only if the joint state, so again, I'm taking the overall state to be pure. It's easy to see this in one direction. If I look at the joint state, if the state is a product state, then this is equal to that, right? And what is the partial trace over B on this state?
Sorry.
Right, because when I take the partial trace, what this is equal to is the trace over B. And this is equal to 1. Okay, so if I have a product state and I marginalize it, then the resulting state, assuming if I had an overall pure state, then the marginal state, also known as, so this state, I'm calling the marginal state, is also known as the reduced density matrix. Okay. I like personally, I prefer to call it the marginal state because it is exactly what it is. It's the state that once I marginalize, the probability distribution gives me the way of calculating the statistics. But often we call it the reduced density matrix, okay? So if it's not, then this thing does not equal this, meaning that row A is mixed. Okay. So I just want to just step back and just think about that for a second and the implications of what that means. What this is saying is that we have a situation in quantum mechanics where we have maximal possible information about the joint system, but missing information about its parts. That's a very odd state of affairs, right? In classical physics, that can't be true. If I know where every particle is, I know the exact position and momentum of the whole, then I know the exact position and momentum of every part of it, of every individual subsystem. There's no way that I can know everything about the whole, but not know about the parts. And this is one of very special features of quantum mechanics, and if this is true, then we say the system is entangled. Yeah,
In what regard does having a mixed state translate to missing information?
that's a good question. Where do you go, folks? How are those things equivalent?
There's an associated ensemble of computer states.
Yeah, and so if a system is mixed, it means we can, as Arik said, that we can think about that as there is some ensemble of pure states that are associated with that mixed state that we prepared with some probability, but we don't know, but somebody does, or somebody could know which of those states was prepared. If I have a mixed state, that itself is a statistical mixture of pure states, and the missing information is this: which of these states was prepared? If I have a pure state, that's the maximum possible information we could have in quantum mechanics. Now, of course, that doesn't mean that every measurement outcome is deterministic. And that's what, of course, is odd. Even if I have 100% complete information, the measurement outcomes are still, can be random. But there is missing information. Yes?
But the randomness that we get from measurements is when you're fighting the uncertainty principle. In theory, you could always get a deterministic measurement of a system that's pure if you measure in the eigenstates, right?
No, it depends if the state is prepared in the as an eigenstate.
I just mean if you know the state and you know its eigenbasis, you could measure and it could be deterministic.
Well, let's think about that for a second. I want to just get the language clear here. I have a state. I measure it in some basis. Let's say this basis is an eigenbasis of some operator A. Okay? Am I going to get a deterministic outcome?
It is non-general.
Let's say it's non-degenerate. So I prepared some state, and I'm going to measure it in the I'm going to measure the observable A, which is to say measure in the basis of its eigenvectors. Am I going to definitely get? Can I predict what outcome I'm going to get? What's the probability of measuring A? It's the probability amplitude squared. Now, if this happened to be an eigenvector of A, we know. But if it's not, we're gonna get a random outcome. So I can have a pure state and know exactly what basis I'm going to measure, but still get a random outcome.
Yeah.
Okay, so just want to be clear on that point. The missing information is in the fact that I don't know which state I prepared. Okay, so if I have a density matrix, and let's say I write this in the basis of its eigenvectors, okay? So let's say that these are the eigenvectors of rho. The fact that I have this probability distribution here is telling me something about missing information about which of these I prepared. Now, how do we quantify that missing information?
Non-zero terms.
Well, that's a very coarse way. I could ask about this mu goes up to 1 to some mu max, assuming that There's some probabilities it might be 0. These are all the non-zero contributions to this. So the number of these is some measure. It's a very coarse measure, but we would want a more fine-grained measure of missing information. How do we do that? Yeah.
When we say that was, max could be, like you could write max as many as you want.
That's
There's a
right.
minimum.
This could be the dimension of the Hilbert space. That's of course, generally, and if I write this will be dimension of the Hilbert space. However, if some of the eigenvalues are 0, then I can truncate the sum up to that maximum value. So if it was a pure state, mu max would be 1, right? Because then it would be the outer product of, it would be the one eigenvector, okay? How do we quantify missing information?
Some of the eigenvalues.
So we could think about it as purity. The purity is one measure, for sure.
The von Neumann entropy?
But often a much more fine-grained picture of it is given by Shannon, right? Shannon taught us how to quantify information in terms of the entropy of the distribution of eyebrows. So we can think about the entropy as the Shannon formula This is the Shannon entropy of the probability distribution of eigenvalues.
Did Shannon write it for quantum mechanics?
No, he was thinking about a probability distribution. I don't think he knew anything about quantum mechanics. So this tells me about the degree of surprise I see if I see a particular measurement outcome. Okay. Now, this formula can be written in a basis-independent way as minus the trace of the operator rho log rho. They're one and the same, because if I write this trace in the basis of the eigenvectors of the density matrix, I'll get this sum. So this formula is known as the von Neumann entropy. They're one and the same. The von Neumann entropy is the Shannon entropy of this distribution. Okay, it's not the Shannon entropy of this with respect to any ensemble decomposition. It's only with respect to its eigenvectors. Okay? So the degree of missing information we measure in terms of the entropy of the marginal. We're going to come to this some more, and this is going to give us a measure of entanglement. Yes?
What's the significance of the negative sign?
Yes. It's because really another way of writing this is this. Okay, so that's really what I'm doing. I'm averaging the log of 1 over the frequencies, which tells us how often we expect that. That's where that negative sign comes from. Okay, I think most of you have probably seen this before, but it's always good to see it again. Think about it some more. All right. So let's look at the simplest example, which has some important implications. Okay, so question. Maybe I'll come back to this. All right. So let's consider two spin 1/2 particles, also known as qubits. So my joint Hilbert space is the tensor product space of the Hilbert space of two spin 1/2 particles, okay? And let's consider a spin singlet, which has total spin 0 and total projection 0. This state, as you remember, is spin up along Z, spin down along Z, minus spin down along Z, spin up along Z. Okay. What are the marginals in this case? What is the reduced density matrix for spin A? So how would I do it? Let's just so this is equal to the trace over subsystem B of the joint state. Which is going to be 1/2 up Z, tensor, down Z, plus down Z, tensor, up Z, minus up Z, down Z, tensor, down Z, up Z, minus down Z, up Z, tensor, up Z, down Z. Right?
Who's gonna do that? Trace though.
Now I need to trace. Trace over B. Okay? Everyone see what I did? I just took the outer product with itself, and now I have to take the trace. So how do I do that? So this guy, when I take the trace, gives me 1. This thing, when I take the trace, gives me 1. This thing, when I take the trace, gives me 0. This thing, when I take the trace, gives me 0. So the marginal distribution here is equal to the maximally mixed state. This is on subsystem A. And similarly, if you did this, because this thing has exactly the symmetry, if I did the trace over subsystem A, I'm going to get the identity as well, meaning a maximally mixed state. Okay? What is the Shannon entropy or the von Neumann entropy associated with these marginal distributions? So it's going to be the log of 2. Now, of course, what base we take, we can choose. Often when we want to think about information, we think about it in bits. So quite often we think about this base 2, which is 1.
Is that what we said? No, that's not an E-bit.
Exactly.
That is.
So that is an E-bit. So what we would say is that this state, the singlet state, has 1 entanglement bit. Or as said, we call that as 1 E-bit of entanglement. Very good. Now, of course, one of the things about, as we said, an entangled state is not a product state by definition, which means that there's correlations, which means that the measurement outcomes, the probabilities of them are not statistically independent. There are correlations. That's what it means to not be a product state. Okay, so entangled states implies correlations in measurement outcomes. All right, so let's just remind ourselves, so let's say we have these two parties, A and B, who are always affectionately known as Alice and Bob. And sometimes C is Charlie. And I used to have in my group Bob and Charlie and Lee. I always wanted Lee to change her name to Alice, but she refused. So then I'm going to have all of them together. Oh well. Anyway, so Alice does a measurement, and so say Alice measures her spin in the Z basis. Okay, and finds, say, up Z. She and Bob got together at the beginning and they prepared these two spins together and they prepared them in the singlet state. And they both know that's how their two spins were prepared. And now, given that she measured the Z basis and found this outcome, what is the post-measurement state? So the state after the post-measurement state we get by the projection postulate. So the state, the joint state of the system, conditioned on Alice measuring spin up, would be the projector onto this, onto the singlet state. And then we have to renormalize. Everyone clear? So this pi here is the projection onto that outcome, okay? And she projects that onto the singlet state and then renormalizes. That's what she would say the joint state is, conditioned on her outcome. And what is that post-measurement state? So we can look at that right up here. The projector on the Z is going to only pick off this term, okay? And then we renormalize it. And so this state is going to be up Z A, down Z B. Which means, as we know, that if she measures this, this is what she would assign as the joint state of the two spins, conditioned on what she saw. And from that perspective, she would predict that when Bob measures his spin, he will for certain find down Z, right? And similarly, we all know if she measures and finds down, then the post-measurement state would be that, right? And so she would predict that Bob for sure is going to see that. And that's not a surprise, they're correlated in this way. There's a correlation.
Should that be an A? Second?
Yes, that should be A. Thank you. Anyway, oh well. All right, so that's fine, but so what? I mean, let's consider the following state. Here's a different state. Which is a mixed state. Okay, this is a state, it's a mixed state. It's not a pure state, but it's not a product state. Okay, this state is, I cannot write this state as a product state of state for subsystem A and subsystem B. Okay? But it's not an entangled state. But what can we say about the same? Suppose we do the same experiment. Okay, so in this case, we're going to do exactly the same experiment. Alice is going to measure in the z basis, and she finds either up or down. If she measures and finds spin up along her system, then she would do the projection take the projection operator, I just write it like this. She would project the state onto her outcome, renormalize, and what would that state be? What's the post-measurement state that she would
The same.
assign?
Shouldn't it be the first term still?
It's just the first term. It's going to be up z on A, tensor down z on B, and vice versa. This is exactly the same as for the spin singlet. And so Alice, if she measures, if Alice and Bob got together and they prepared this state, and Alice measured her spin along the z direction, and she found spin up along z, then she would predict, even if Bob is on the other side of the galaxy, that Bob is going to find spin down along z. And she can predict that instantaneously. But this state is not entangled. This is what we would call classical correlations. It's like this. Okay, here we go. I have a red, orange chalk and a blue chalk, and Shri is going to get one of these. Don't tell anyone. Close your eyes. Remember, there's an orange and a blue. Okay, open your hand. What color do I have?
Orange.
Yeah! Magic! Right? Magic. She instantly predicted what I was going to see. Oh, that was an amazing experiment. They were classically correlated. So what's the difference? What would we measure? I mean, the fact that, this drives me absolutely nuts about the way people think about that. Of course, when things are correlated, you can make predictions about things that are not causally connected because you knew about those correlations. It's not that I forced anything to happen. Come back to the distinction between that soon, but let's just so, question, what is for that we just wrote over there? What are the marginals? So if I take the, if I marginalize, I trace out B in this case, what is the state of that Alice assigns to her spin?
Identity.
The identity. That's to say, the completely mixed state. And similarly for B. It's exactly the same thing we had as in the singlet. So again, the pieces don't tell me everything about the whole. If I just, so let's just think about what this means for a moment. What this means is that if Alice or Bob do a measurement on their local subsystem, on their spin, no matter what basis they measure in, whether they measure in X or Y or Z or any other basis, they see a random outcome. They see either up or down random. And that's true whether we prepared the spin singlet, which also had those marginals, or this mixed state, this classically, the Sri-Ivan correlated state, that we randomly saw either purple or red. We didn't know, and it was a completely random outcome, but there was a particular correlation between them. So what distinguishes these things? If we see the same correlation that we just saw in the Z basis, and they also see the same local randomness, what's different about these things? Yeah?
Is it the capacity to exhibit like interference?
Interesting, yes. I think that's it's a good way of thinking about it. And how would that manifest itself? So what we just described here are a set of measurements which show exactly the same measurement statistics. The measurements associated with the local measurements that either Alice and Bob did, and the correlations that they saw when we measure in the Z basis. Yeah?
Correlated measurements?
Well, of course, we could also think about what is the correlations between those measurements, but I want to think about this from the point of view of when Alice measures something, her ability to predict what Bob is going to see. The ability, I made this, we just closed our eyes, we measured the chalks, and there was nothing special about that. But there is something special that's different from this classically correlated state compared to the spin singlet. Yeah?
If Alice entangles a new bit with the entangled one, and they're now all three entangled in a way, like teleportation.
We could, of course, I'm not going to be able to teleport with this, that is for sure. It's a little extra. I want to do something similar. Let's do a different experiment. Suppose Alice measures in the X basis. she's gonna measure sigma x, which has an up x or a down x. Okay? Suppose she does that. What would she predict Bob sees?
In X,
No, what, in terms of what state she would assign to Bob. So let me try to be clear here. Alice does this measurement, and post-measurement she wants to say, so let's say we have a singlet. That's written up there. And now she measures in the x basis. And conditioned on that measurement, say she finds spin up along x. Okay? What is the post-measurement state? Well, what I get is I do the projector on the state. And then I renormalize.
Bob will have either if you measure up x, Bob will measure down x, and vice versa.
Excellent. Let's see how it works. Okay, so this is given by the projector along x, up x, on this state, which is 1 over root 2 up z, a down z, Bob, minus down z, Alice, up z, Bob. And then we normalize, right? So this is my spin singlet state, and I'm doing this projector, and then I'm going to renormalize. What do I get? Well, I'm going to get the inner product of up along x with up along z, which is 1 over root 2. And then I get the inner product of up along x with this, which is also 1 over root 2. And so it's going to be a whole 1 over root 2, and then I renormalize that. And so this is going to be equal to up along x times 1 over root 2 down along z minus up along z, which is
The minus of the down x.
minus, right. Now that overall sign is an overall phase. I don't really care about it.
Won't it be down because it's an antisymmetric mixture?
Say again, Tristan.
We should, down along B, yes, sorry, I read here.
Right? So, what that means is that if Alice does a measurement in the x basis, and she finds up along x, she will predict for sure that if Bob were to also do a measurement in the x basis, without a doubt, he's going to see down along x, okay? What about for the mixed state? So Alice does this measurement along the x basis, and she finds up along x. What would be the post-measurement state conditioned on that outcome? I do the projector on each of these states. So I have to project this guy onto the x basis and this guy onto the x basis. When I do that, I'm going to get the same value. I'm going to get a half and a half. And then I renormalize it, and that gets rid of that half. So what you would see which you would write Everyone clear on that? So Alice measures her spin. She does it in the x basis, and she finds spin up along x. Condition on that measurement, she says, I knew I was prepared in this correlated Sri-Ivan state, and I know how to do the rules of quantum mechanics, and this is what I would say is the post-measurement state conditioned on what I measured. Is this the same thing as this? No. In fact, what would she say about Bob's outcome? If Bob were to measure in any basis, it would be completely random. There's no correlation in that case between the X measurement that Alice does and any other measurement Bob would do. So there's a very different, this thing is no longer, the measurement outcomes are not correlated. Whereas here, they were completely correlated. So there's something different between those classical correlations, which can have correlations, but there are stronger correlations that are possible with the entangled state, which is kind of coming from this interference that you were suggesting, that are just not possible, okay? So, we'll just end there. I just want to make just one statement here that generally, a classically correlated state which is sometimes called separable. I hate this term for a reason I'll explain in a moment. We would say is a statistical mixture of product states, okay? So if the state is classically correlated, it means that I have, this is not equal to so if this probability distribution does not factorize, we say it's classically correlated, okay? If it can be written this way as a statistical mixture of product states, then we say it's separable. I would prefer to call this unentangled. What's the difference? Because I can have a separable state that is not a product state, right? This is classically correlated, but we use the language it's separable because it's not entangled, okay? But it's really unentangled. It's really a product state only if this thing, okay? So otherwise, it's entangled. So, what we're going to do to remind ourselves is what is special about the correlations that can exist in an entangled state that are not possible for an unentangled state or a separable state. We saw just a taste of it here in the context of the distinction between the singlet state and the triaden state. Okay, this mixture state. This state shows correlations. It's just that the correlations are different. So they're very powerfully different. And that's what we'll remind ourselves of when we talk about bells and Collins on Thursday. All right? Very big day. It's good to review some things. Have a good afternoon.
Already measured number of qubits for the mixed state. Is that, would it be different?
Interesting question.